All evidence and theories suggest that the Moon was formed from a collision with Earth. For ages, the Moon has been a calm presence in the night sky. However, recent observations indicate that it is experiencing alarming changes. Seismic activities and mysterious surface changes hint at a potential disaster. Could these lunar shifts trigger catastrophic events on Earth? What chain reactions might we expect from our celestial neighbor? Most importantly, how could these changes impact life as we know it? Join us as we explore the Moon's terrifying transformation that could provoke a major disaster on Earth. The Apollo 11 mission was a monumental leap in space exploration, not only for landing the first humans on the Moon but also for bringing back invaluable samples of lunar rock and dust. The astronauts returned to Earth with approximately 1.6 kilograms of this material, which soon became the key to unlocking the mysteries of the Moon's origin. Upon analyzing these samples, scientists discovered that the lunar rocks date back around 4.5 billion years. This finding was groundbreaking, providing the first concrete evidence that the Moon formed roughly 150 million years after the birth of our solar system. This era is now regarded as one of the most chaotic periods in our solar system's history. Astronomers believe that during this turbulent time, the inner solar system was teeming with around 20 small planets that frequently collided, eventually forming the 4 terrestrial planets we know today: Mercury, Venus, Earth, and Mars. One of these cataclysmic collisions is thought to have given birth to the Moon. The leading theory, the impact hypothesis, suggests that the Moon's formation resulted from a colossal collision between Earth and a Mars-sized celestial body named Theia. When Theia collided with Earth, it shattered into countless fragments. These fragments, along with vaporized rocks and gases from Earth's mantle, merged over millions of years into a molten sphere that eventually solidified into the Moon we see today. Recent research, however, presents a compelling twist to this long-standing narrative. New evidence suggests that the Moon might not have formed gradually over millions of years but instead emerged in a matter of hours. The traditional hypothesis assumes that the Moon is primarily composed of material from Theia. However, the analysis of lunar rocks challenges this notion. The chemical composition of these rocks closely resembles that of Earth's rocks rather than those of a foreign celestial body like Theia. Furthermore, the isotopic signatures found in lunar samples are strikingly similar to those found in terrestrial rocks but markedly different from those found on Mars or other parts of the solar system. This evidence strongly indicates that much of the Moon's material originated from Earth. Another intriguing piece of the puzzle is the alignment between Earth's spin and the Moon's orbit, both having similar orientations. This detail further supports the idea that the Moon is largely made up of material from Earth. This alignment is difficult to explain if the Moon were primarily composed of Theia's remnants. These new findings have led some astronomers to propose that the Moon's formation was not a slow and gradual process but rather a rapid event. One theory suggests that the impact between Earth and Theia was so intense that it caused a massive explosion, flinging material into space at tremendous speeds. This material could have coalesced into the Moon in a very short time frame, possibly within hours. Such a scenario would explain why the Moon and Earth share so many chemical and isotopic similarities. If the Moon did form rapidly, it would reshape our understanding of planetary formation processes. This rapid formation theory could mean that other moons and planetary bodies in our solar system might have formed in similar ways, challenging many established ideas about how planets and moons develop over time. To explore alternative scenarios for the Moon's formation following the colossal collision, researchers turned to a powerful computer program called SWIFT. This sophisticated software is designed to simulate the complex gravitational and hydrodynamic forces that come into play during and after such a monumental impact. The research team used a supercomputer named COSMA to run these intricate simulations. Simulating these violent collisions is no simple task. The process requires continuous testing and refinement until the increased resolution of the simulations no longer alters the results. This level of detail is crucial for obtaining accurate and reliable data. Given the complexities involved, the team conducted hundreds of simulations of Earth-Theia collisions. They varied the angles, spins, and speeds of the impacting bodies in their models. Additionally, they simulated up to 100 million particles to represent the matter involved in these cataclysmic events. These high-resolution simulations provided a more detailed view of the impact dynamics than ever before. The results of these simulations were remarkable. Contrary to the long-held belief that the Moon took millions of years to form, the models suggested a much quicker process. Within just a few hours, the Moon coalesced from the debris ejected from Earth and the shattered remains of Theia. This finding challenged previous theories about the Moon's formation timeline. Moreover, the simulations revealed that a significant portion of the material used to form the Moon's outer layers originated from Earth. This insight provided a deeper understanding of the Moon's composition and its relationship with our planet. The models showed that Earth's material played a crucial role in shaping the Moon's structure, further emphasizing the interconnectedness of the two celestial bodies. The high-resolution simulations conducted using the SWIFT program and the COSMOS supercomputer have revolutionized our understanding of the Moon's formation. By modeling hundreds of Earth-Theia collisions with different angles, spins, and speeds, and simulating up to 100 million particles, researchers achieved unprecedented levels of detail. These simulations showed that the Moon could form within just a few hours, a significant departure from the previously held belief that it took millions of years. The discovery that a significant portion of the Moon's material came from Earth provides new insights into the Moon's composition and its relationship with our planet. The models indicate that Earth's material played a crucial role in shaping the Moon's structure, highlighting the deep interconnectedness of the two celestial bodies. The rapid formation of the Moon, as suggested by the simulations, implies that the process was much more dynamic than previously thought. This has profound implications for our understanding of planetary formation in the early history of our solar system. The insight that the Moon's material largely originated from Earth also suggests that the Moon is not just a satellite of our planet but an extension of it, formed from Earth's very substance. To further investigate and confirm this new theory, scientists are focusing on obtaining more detailed data from the Moon's mantle. This involves analyzing rock and dust samples from deep beneath the Moon's surface. Such samples will provide crucial information to verify the simulations and offer a clearer picture of how the Moon has evolved over billions of years. Accessing these deep lunar samples is a challenging task, but it remains a key goal for ongoing and future lunar missions. The more samples scientists can analyze, the better they will be able to confirm the accuracy of the high-resolution simulations and refine their understanding of the Moon's formation. This research will not only enhance our knowledge of the Moon's origins but also shed light on the broader processes of planetary formation and evolution within our solar system. Over its 4.5 billion-year history, Earth has been relentlessly bombarded by asteroids, eroded by wind and rain, blanketed by flowing lava, and reshaped by tectonic shifts. These processes have erased most traces of our planet's distant past. However, there is a celestial body where these ancient clues remain largely intact, the Moon. By meticulously studying the Moon's surface, mapping its mountains and craters, and probing its interior, scientists are uncovering valuable insights into the early history of both the Moon and our own planet. The Moon acts as a historical archive, preserving the record of its formation and the events that shaped it. Unlike Earth, the Moon lacks an atmosphere and active geological processes that would erase its ancient history, making it an ideal place for scientists to search for evidence about the early solar system. By examining lunar rocks and soil, scientists can piece together the story of the Moon's birth and, by extension, gain insights into Earth's beginnings. The advent of the space age brought with it the technology to launch humans and their life support systems into space. Over 300 manned space flights have demonstrated that humans can live and explore beyond our planet. Among these missions, the Apollo program stands out as a defining moment in our connection to the cosmos. While the primary goal was to demonstrate technological prowess during the Cold War, the scientific legacy of Apollo has far surpassed its original political motivations. The Apollo missions, driven by the intense rivalry of the Cold War, were initially seen as symbols of technological and ideological superiority. The successful landing on the Moon was a profound achievement, symbolizing human ingenuity and resilience. Many envisioned that this would be the precursor to further exploration of Mars and the eventual habitation of space. However, these ambitions proved too grand against the backdrop of political, social, and economic challenges on Earth. Despite the geopolitical motivations, the Apollo mission's most enduring legacy lies in the scientific treasure trove brought back from the lunar surface. When Apollo astronauts stepped onto the moon, they entered a world coated in fine, sticky dust and scattered with rocks and craters. During their explorations, they collected 382 kilograms of lunar rocks and soil samples, which they brought back to Earth for analysis. Back on Earth, scientists began meticulously analyzing these samples, searching for answers to one of the most intriguing questions in science: how did the moon, and by extension, Earth, come to be? These rocks, some billions of years old, contain a wealth of information about the conditions of the early solar system. By studying their composition, scientists can infer the processes that led to the formation of the moon and the nature of the primordial Earth. The detailed study of lunar rocks has provided crucial insights into the violent history of our solar system. These samples have revealed evidence of a massive collision between the early Earth and a Mars-sized body, a hypothesis supported by high-resolution simulations. This impact, which is believed to have formed the moon, also significantly influenced the geological and atmospheric evolution of Earth. The similarities in the composition of Earth and moon rocks suggest that much of the moon's material came from Earth, reshaping our understanding of this celestial relationship. The lunar samples collected by Apollo astronauts remain a vital resource for scientists. They offer a direct link to the processes that shaped our solar system billions of years ago. Continued study of these samples, coupled with new missions to gather more data, will enhance our understanding of the moon's formation and its impact on Earth's history. As we delve deeper into the secrets of the moon, we not only uncover the story of our celestial neighbor but also gain profound insights into our own origins. These rocks showed that heavier materials sank towards the moon's core, pushing lighter materials to the surface. The rocks brought back to Earth were surprisingly similar to rocks found on Earth, with specific oxygen isotopes that scientists compare to blood types for solar system bodies. Initial observations suggested that the moon was completely dry, with no evidence of water ever being present on its surface. This changed our understanding of the moon's formation. After the last Apollo mission in 1974, scientist and artist William Hartmann proposed a revolutionary idea. He suggested that the moon formed from the debris of a massive collision between Earth and a body named Theia. This event occurred when Theia's orbit became unstable, causing it to crash into Earth at an angle. The impact made Earth spin faster, and debris from both bodies was flung into orbit, eventually forming the moon. During this violent process, volatile compounds like water evaporated, leaving the moon dry. The moon's composition primarily comes from the mantle of both Earth and Theia, which explains why it's less dense than Earth. While the moon has a solid iron core like Earth, it's relatively small. From this tumultuous beginning, the moon gradually cooled, and the molten surface solidified into a crust. However, the moon continued to endure intense bombardment in the chaotic early solar system, leaving its battered surface evident in a global elevation map compiled by the Lunar Reconnaissance Orbiter. The Apollo astronauts encountered rocks formed from widespread volcanic activity, shaped by ancient volcanic processes. These rocks tell a story of a once dynamic lunar environment. Craters and lava plains explored by the astronauts provided clues about the moon's volcanic past, revealing that it wasn't always the cold, desolate place it is today. Recent studies have shed light on the moon's geophysical properties. Seismic data from the Apollo missions revealed that the moon experiences moonquakes, thought to be caused by tidal forces exerted by Earth's gravity. The moon's lack of atmosphere means its surface is directly exposed to space weathering, with micrometeorite impacts and solar wind gradually altering the lunar surface, creating a fine layer of dust known as regolith. Volcanic eruptions on Earth are often fueled by water, but lunar volcanoes are linked to impacts forceful enough to melt the surface and release material from the hot interior. In the lower gravity of the moon, volcanic eruptions would have taken on a different form, splattering molten rock high above the lunar landscape, creating thin, smooth layers extending far from the eruption source. These layers formed the Maria regions, covering about 1/6 of the moon's entire surface. Scientists believe these immense volcanic basins originated from large and violent impacts that occurred 3 to 4 billion years ago. Materials brought up by these impacts are composed of heavier compounds that would have initially sunk into the magma ocean. Modern technology, such as LRO cameras, has helped scientists detect volcanic residues in recent impacts, providing valuable insights into the moon's volcanic history. One intriguing lunar feature is the Aristarchus Plateau, which showcases a mysterious channel carved by flowing lava. Another fascinating landscape is the Tycho crater, resulting from an impact approximately 100 million years ago. The Moon's influence on Earth goes beyond its geological history. Its gravitational pull affects Earth's rotation, stabilizing it and promoting the formation of ocean currents that shape our climate. The relationship between Earth and the Moon, rooted in a violent collision long ago, is a fascinating aspect of planetary history. However, not all aspects of the giant impact theory are universally accepted. One point of contention is the presence of water on the Moon. The dryness of the Moon aligns with the giant impact theory, suggesting that water and other volatile compounds would have evaporated from the lunar debris cloud. However, recent findings challenge this notion, indicating that the Moon may not be as dry as previously believed. In fact, about 5.66% of the crater floor was found to be composed of water ice, marking a higher concentration than some areas on Earth. This discovery of water on the Moon opens up exciting possibilities for future explorers envisioning spending extended periods on our celestial neighbor. How did the water end up on the Moon? One idea is that it arrived over countless ages through common impacts. However, another theory emerged from rocks collected by the Apollo astronauts. These rocks contain tiny glassy globules, minerals that melt in the intense heat of lunar volcanoes. Scientists have detected a compound known as hydroxy in these rocks, which could potentially be converted into water, valuable for sustaining a Moon base. It's believed that much of the Moon's original water was lost to space due to impacts. However, there could be remnants of water in the Moon's polar craters. Additionally, a significant amount of water might still be trapped inside the Moon, possibly enough to form a 1-meter-deep layer across its surface. The discovery of water inside the Moon raises questions about its formation. Some researchers propose that water was brought in by comets during the Moon's early formation, rather than being present since its inception. A recent study suggests that the formation of the Moon involved a more complex scenario than previously thought. According to this theory, a smaller celestial body formed alongside the Moon and later merged with it due to a colossal impact event. This impact reshaped the Moon's interior, causing molten magma to flow onto the near side and adding a layer of crust to the far side, explaining the uneven terrain of the Moon.